All right, we have arrived at week 3. And for those of you that feel like this isn't really a math class because we haven't actually been doing that much math, I am glad that I'm not going to let you down, because this is where the mathematical part of statistics really begins. Numerical displays of data. How to summarize, using descriptive statistics, how to summarize a bunch of data with just 1 or 2 numbers. That's what we're going to look at today. But before we get too far into that, we want to make sure we clarify the difference between a parameter and a statistic. This we talked about in week 1. A parameter measures the entire population. Everybody is calculated into a parameter. And why that's important is as long as the population is unchanged, the parameter is also going to be unchanged. If I talk about the average age of everyone in the United States, that's a population. That's everybody. That average age is not going to change as long as nobody dies and nobody's born and nobody gets older. If we take a snapshot in time, that average age is going to stay the same. It's a population parameter. When using populations and parameters, we will always represent them with Greek letters. 2 common Greek letters, we're going to see them later today, are the first one here is the Greek letter mu, kind of like a cow, but a little different, mu, or the Greek letter sigma. Both of these have very important meanings in statistics, and we'll get to those later. Now, a statistic is a measure that is calculated from a sample that is selected from the population. What's different about this is that the value can change based on which sample is selected. If we're talking about the United States, and I take a sample from the state of Washington, I'm going to get a different average age than a sample in the state of Missouri. Different samples are going to reveal different statistics. The parameter about the whole population, though, will always remain unchanged. For these sample statistics, we use English letters. A common one is X bar. We put a little bar over the X to say this one's special, a special type of X, and we'll talk about it in a minute. And the letter S are 2 common ones that we will see today. So parameters, entire population, statistics, small sample. Okay, so if we're going to represent the entire data values out there, we are going to find some type of measure of center. So we can talk about this average person, or average sale, or average quality control result. Average is kind of a vague term. It's got actually 3 common meanings in statistics. The most common you hear is the mean, and that's where we divide the sum of the data values by the number of data values. And you've probably done this before. It's probably what we think of when we hear the term average. The median is the middle data value when we put all the data in order. We've got half of the values are going to be bigger than the median, and half of the values are going to be smaller than the median. Next is the mode. The mode is the most occurring data value, the most common response, the most common result is your mode. Let's take a look at each of these in a little bit more detail with an example to go along with them. First, the mean. When we're talking about the population, the mean of everyone or everything, we're going to use the Greek letter mu. The Greek letter mu will always talk about the population. When we're talking about a sample, we're going to put a line over our variable x. It's read x bar. X bar is the mean of the sample. Both of them are calculated the same way, though. We take the sum of all the values and divide by the number of values. This capital letter sigma here, it means sum. This means add up all of the x's. Add them all up, and then divide by how many there are. So let's say I run a boat rental company, and this week I keep track of my boat rentals. On Monday I rented 6, Tuesday 8, Wednesday 3, Thursday 6, Friday 12, Saturday 29, Sunday 19. You can tell boat rentals, as you would imagine, the weekend is a better time for the business. Now, if we wanted to calculate the average number of boats rented a day, we simply have to add up all these values and divide by the number there are. So assuming we're talking about a week is the entire population, we're going to add every single value together. 6, 8, 3, 6, 12, 29, 19. That's going to give me 83. And we divide by the number of data values we're talking about. Dividing by 7 gives us an average of about 11.86 rentals per day. That's the mean. Add them up and divide by the number of values. The median, as we said, is the middle data value when all of them are put in order. Sometimes when we do this, there'll be two values in the middle, not just one that stands alone. In that case, what we'll do is we will find the middle of the middle, or the average of those two data values. Add them together and divide by 2 to get us right in the middle. So again, talking about my boat rentals, we're not asking for the middle day, otherwise it would always be Thursday. We're talking about the middle data values. So first we have to put all the data in order. So the smallest, 3, then we had 6, 6, 8, 12, 19, and 29 in order from smallest to largest. Then we want the middle value. Notice we've got 3 on each side, and then the middle value of 8. 8 is our middle value, so 8 is our median. And what this means is half of the time I'm going to have less than 8 rentals, and half of the time I'm going to have more than 8 rentals. That's the median. It tells us where we are with half above and half below. Let's do a quick example though, stepping away from my boat rentals. What if we have 2 in the middle? Let's say I'm looking at a real estate company and they're tracking the number of houses that are on the market each month. So in January there's 4, February there's 7, March there's 9. Gets busier in the summer, slows down into the winter. We might be looking at a specific neighborhood of interest or something. Well, if we want to find the median number of houses on the market in this neighborhood, when half of the time there's more and half of the time there's less, we first have to put them in order. So we'll go through our data values and say, well, first there's 4, then 6, 7, 9, 11, 14, 17, 28, 31, 39, 42, 46. And then if we come in 1, 2, 3, 4, 5, 6, from each side, 1, 2, 3, 4, 5, 6, we see there's 2 values that are actually in the middle, 14 and 17. Well, we can't have 2 medians, so what we'll do is we'll add those values together. 14 plus 17 is 31, and divide by 2 to get 15.5. And so we'll say half the time there's more than 15.5, and half the time there's fewer than 15.5 houses on the market. Median is the middle. Mode. Mode is the data value that occurs the most often. And it's often we are asked for the mode of a bunch of numbers. And that's not really a good use of mode. It is usually used in qualitative data. Like if we ask, what is the most common color of a car? What is the most used credit card by our customers? What is our customer's favorite restaurant? What is that most often result in categories? That's where we start talking about the mode. So we've got our boat rentals. Like I said, for some reason we do data values, and here I go doing exactly what I was complaining about. But just so that we can compare what we've been talking about, we can see that twice 6 were rented. So the most common response then, I guess, is 6. The mode is 6 for my boat rentals. So as a comparison, my boat rentals have a mean of 11.86, a median of 8, and a mode of 6. So which one do I use? Which one's better? Well, the answer to that question is, it depends. Let's look at the advantages and disadvantages of each of these three measures of center. First, the mean. The advantage of the mean is it's really easy to calculate. It's the common thing we think of when we hear average. Everyday lay language, every person will think about the mean when you start talking about the average. The disadvantage of the mean, the negative, is that an extreme value can distort the value. If you remember going back to our results, the mean was much higher than the median because on the weekend I had a lot more boats being rented than on the weekday. An extreme value can distort the mean and make it seem bigger or smaller than a real center would be. So what about the median? Well, the advantage of the median is it's not affected by extreme values. It's only affected by how many are above and below the middle value. The disadvantage is it's difficult to find for large data sets. It can take a lot of time to put data in order. It can take a lot of time to make sure you're in the direct middle. It's just not a very convenient middle value. So what about the mode? We already said the advantage is it's great for qualitative data. If we're talking about our customer's favorite style of music, we can't really say the add up pop plus rock plus disco and divide by 3 and come up with an average music that people like. You can't do that with qualitative data. So the advantage is we can talk about a mode, which is the most common preference of our customers, or most common response in a survey. The disadvantage, it's not really useful for quantitative data. Knowing that I did 6 boat rentals more often than any other number didn't really mean anything in terms of my bottom line because that might have just been 2 days out of the entire lot and all the other ones were different. It's just not very useful to use the mode in that situation. So we've got 3 styles. Who wins? Well, at least in statistics, the mean is what we use the most, which is probably why we have a Greek letter and an English letter attached to them. The mean of the population, the parameter is mu. The mean of the sample, the statistic, is x bar. We're going to use mean a lot. However, there is a problem if we just use the mean. Let's take a look at a couple companies. Let's say we're talking about the number of employees in a company, and we're trying to see how successful the company is. So company A has 25 employees in January, 25 employees the next year, 25 employees the next year. 3 years in a row, they've gotten 25 employees. Well, on average, you might imagine, 25 plus 25 plus 25 divided by 3, there's an average of 25 employees at this company. It's probably staying pretty consistent, pretty predictable. Well, what about another company? Another company has 23 employees, then 25 employees, then 27 employees. The average is 23 plus 25 plus 27 divided by 3, which is 25. We can even take a more extreme situation. A third company has 3 employees one year, 27 employees the next year, and 45 employees the next year. Business is booming for Company C. It is growing, it is expanding, it is adding to the workforce, but the average is 3 plus 27 plus 45 divided by 3 is 25. All 3 of these companies have the same average number of employees over the past 3 years. But clearly all 3 companies are not the same. So we need a way to differentiate between not just the center or the average or the mean, but also how spread out the data is, because they are not the same. So let's talk about spread, how spread out the data is. How dispersed the data is. Are they close together? Are they far apart? This is spread. And there's 3 common measures of spread that you hear about: the range, the variation, and the most popular, the standard deviation. But let's look at each of these 3 individually. First, the simple one is the range. And basically all we do with the range is we want the distance between the largest and the smallest value. Take the big number, subtract the small number. That's the range. So for company A, 25, 25, and 25, the biggest was 25, the smallest was 25. There's no range, 0. There's not really any dispersion or spread. Company B, the largest value was 27, the smallest value was 23, and so when we subtract, we get 4. So there's a slight range. Company C, though, when we take 45, the big value, and subtract 3, we get a range of 42, a much larger range for company C, implying that those are probably more spread out. But range isn't really very ideal. We don't use it a lot because it's only based on 2 data values. And what if one of those data values is a large outlier and everybody else is kind of grouped together? Then that range is not going to be very accurate because there's lots of values clumped together and only one value way out there. So we need a better method. And that's where this idea of variation comes from. Variation, when we're talking about a population, we'll use the Greek letter sigma squared. And this is important. Variation's got this squared on it. Sigma squared. If we're talking about the variation of a sample, we use the English letter S. S squared is the variation of the sample. And that's the one we're going to work with the most. In actual practice, we don't really ever know the variation of a population. We can kind of guess it. And we'll talk about ways to guess it and estimate it when we get to inferential statistics. But for now, we're going to just use S squared for the variation of the sample. And it is the average of the squared distances from the mean. That sounds weird. Maybe we should look at a math equation. It is the sum of the difference between the mean and the data values squared divided by n minus 1. Whew! That looks weird too. I don't want to scare you with this equation because it's actually a really easy equation to work with. We're going to work with it in just a minute, but I just want to make sure we understand what's happening. Basically, what we do is we take every single number, subtract the mean, square the answer, and add them all up. And then we have to divide by 1 less than the number of data values. Okay, let's actually look at how we can make a table. We're going to make a table for every step along the way. And this is how I want you to be able to solve these. When I ask you to find the standard deviation on your own, I'm going to give you only a few data values. When there's a lot of data values, we're going to go ahead and use Excel to help us out. But when there's a few data values, it's quite manageable. What we'll do is we're going to make a column for each of the data values, a column where we list the mean. The mean doesn't change, so it's going to be the same all the way down. And then we're going to subtract. The value minus the mean gives us a number. The value minus the mean gives us a number. The value minus the mean gives us a number. These numbers are always going to add up to 0, so that's not going to be useful to us because some are going to be negative and some are going to be positive. So what we will do is we will square each of those numbers, which will make them positive. Then we can add them all up. So when we add them all up, what that's going to do is that's going to give me the sum of the data values minus the mean squared. And then we will find the variance, which means we just take that value that we just found and we divide by 1 less, if I can write on my screen, 1 less than the number of data values. Maybe it's coming together a little bit. Let's actually do it with some data values. Let's look at Company A. Company A had 25, 25, and 25. The mean of company A, we already calculated, was 25. And the mean always stays the same all the way down. Then what we're going to do is we are going to subtract. 25 minus 25 is 0. 25 minus 25 is 0. 25 minus 25 is 0. This is a really boring example because all the values are the same. We'll get to a more interesting example here in a minute, but let's work this all the way through just so that we can see the steps. The last column, we square our values. 0 squared, 0 times 0 is 0. 0 squared is 0, and 0 squared is 0. We're going to add those values together. Told you this was a boring example. 0 plus 0 plus 0 is 0. To find the variance, we take the value we just got and divide by 1 less than the number of data values. There are 3 data values minus 1. That equals 2. So we are going to divide by 2. 0 divided by 2 is 0. The variance of company A is 0. Okay, that was boring. Let's do company B here. They're a little more interesting. Company B was 23, 25, 27. Now, we've already talked about the average of them being 25. We already calculated that. Write in your average all the way down. And then subtract. 23 minus 25 is negative 2. 25 minus 25 is 0. And 27 minus 25 is 2. Now we square each of these data values. 2 squared is 4. Notice a negative times a negative is a positive, so it should always be positive over here. 0 squared is 0, and 2 squared is 4. Add those all up to get 8. So what we'll do to get our variance, s squared, we take that value we just found of 8 and divide by 1 less than the number of data values. There are 3. We subtract 1, and we get 2. 8 divided by 2 is 4. The variance of company B is 4. Now, the really interesting one is company C. What's its variance going to be? Because these guys are spread out all over the map. We would expect to see a much larger variance for company C. And sure enough, we will. The mean we already calculated is 25 all the way down. And then we subtract. 3 minus 25 is negative 22. 27 minus 25 is 2. And 45 minus 25 is 20. Now we're going to go through and square those values. We might need a calculator because these numbers are getting big. 22 squared is 484. 2 squared is 4. And 20 squared is 400. Add all those up, and we get 888. Variance is that number we just found divided by n minus 1. Again, there are 3 data values. Subtract 1, and we get 2. 888 divided by 2. The variance of company C is 444. Comparing all 3, the variance of company A, 0. The variance of company B, 4. And the variance of company C, as we would expect, much larger, 444. Now, there is a problem with the variance that we like to fix, though. If you remember when we were calculating the variance, we squared each of our data values. So really, the variance kind of has the squared element to it. It's nice if we can get rid of that squared element. And that's where we come up with the standard deviation. And this is the one we're going to see the most. It's the square root of the variance. With population standard deviation, we just have sigma. With sample standard deviation, we just have s. Notice the squared part is gone. Now it's the square root. We're just talking about the standard deviation. And so really, the short way to calculate the standard deviation is we take the square root of the variance. Or we can just take the square root of the big formula, which basically just means if we're doing our columns, we have to take the square root of our solution. So standard deviation, you have to take the square root at the end. For our example, company A, we already calculated the variance is 0. Square root of 0 is 0. Company B, we calculated the variance to be 4. So the square root of 4, the standard deviation is 2. Company C, we calculated the variance to be 444. So the square root of the variance is 21.07. And these are the standard deviations of the companies. Now, standard deviations we use a lot to talk about how far away from the mean a certain value is. And one reason for that is we have this thing called the empirical rule. Now, a little context here. This guy is called the bell curve. The bell curve says that if we've got the mean right here in the middle, and we make a histogram for a bazillion data values, we're going to have a lot more frequency close to the mean. Notice it's really tall. And the farther from the mean you get, the fewer and fewer frequencies. The idea is if the average height is 65 inches, most people are going to be around 65 inches. A few people are going to be short and a few people are going to be tall, but most people are in here in the middle. In fact, it has a lot to do with the standard deviations. If I move to the right 1 standard deviation, so mu plus 1 standard deviation, and I move to the left 1 standard deviation, mu minus 1 standard deviation, in between these 2 points, turns out we will get 68% of our data values, assuming that they're spread out normally. And we'll get more into that later. But for now, 68% of the data values generally will fall within 1 standard deviation of the mean. In fact, if we extend that out and we go out 2 standard deviations, mu plus 2 sigma, and backwards 2, mu minus 1, 2 sigmas, from this point all the way across to this point, you're going to actually end up with 95% of your data values. Basically, 19 out of every 20 people, objects, products, responses are going to fall within 2 standard deviations of the mean. In fact, you can go out further all the way to 3 standard deviations on each side. And basically, when you go out 3 standard deviations, you pretty much have everyone. Well, okay, not everyone, 99.7% of the data. So 3 out of every 1,000 responses will be outside of 3 standard deviations. That's pretty extreme. And so what's nice about this is it lets us talk about how many standard deviations away from the mean is a certain value. It's kind of like now we have a way to tell temperature. How many degrees away from 0 is the temperature? If it's 17 degrees positive, that means it's 17 steps ahead of 0 degrees. If it's 17 degrees negative, it's 17 steps to the left. Temperature takes this point of 0 and a certain measure up and down. Standard deviations do the same thing. We measure from our central point, which is the average, and we either are positive or negative, above or below the mean, this many standard deviations. Finding out how many standard deviations away something is from the mean can be very useful to us in our study of statistics. And we're going to talk about this a lot as this course develops. Basically, if we're saying if z is the number of standard deviations from the mean, then we can take the mean plus the number of standard deviations times the standard deviation is going to equal any data value. Now, what's interesting to us in this equation is the letter z. We want to know how many standard deviations away something is. So we're going to solve this formula for z. We start by subtracting mu from both sides. Gives us x minus mu equals z sigma. Divide both sides by sigma. And z, the number of standard deviations away, is x minus mu divided by sigma. It works exactly the same for x bar. That's a really small bar on this x, but that's x bar right there. We take the value minus the mean divided by the standard deviation. Now we've got a standardized way to compare what seems to be different things. Here's an interesting problem. I'm a district manager for over 3 plants. My local manager at plant A has averaged over the past year 700 units with a standard deviation of 200. Now, this month, he came up with 810 units, so he improved. That was good. At plant B, they're bigger, they're more efficient, they've got more technology. They average 2,300 units per month with a standard deviation of 350. But this month, he pulled off 2,600 units. Plant C averages 1,200 units per month with a standard deviation of 30. They pulled off 1,320 last month. So who's most improved? The common error that a lot of regional managers run into is they say, well, Plant B improved the most. He increased 300, 2,300 to 2,600. That's definitely the better manager. He is getting the most done. Well, maybe he's getting the most done because he's got the best plant, the best technology, more employees than the other managers had to work with. So let's look at how many standard deviations each one improved. That standardizes the level of measurement so everyone is compared on the same scale. So for plant A, we take the data value, 810, subtract the mean, 700. We get 110 divided by the standard deviation of 200. Ends up with 0.55, just over half a standard deviation of improvement for plant A. Same thing for plant B. We take the data value, 2,600. We subtract the mean, 2,300, divided by the standard deviation of 350. So 300 out of 350, he increases 0.86 standard deviation. So he did do better than plant A. But what about plant C? Plant C, if we take the data value of 1,320 and we subtract the mean of 1,200, we get 120 divided by the standard deviation of 30, and they have increased 4 whole standard deviations. Remember the empirical rule? 99.7% of my plants are within 3 standard deviations. This guy pulled off 4 standard deviations. He is in the top of the top. Plant Manager C is clearly doing a much better job with what he has in his plant. So that's one way we can compare what seem to be different situations by standardizing the measurement. How many standard deviations away are we from the mean? So in summary, we talked about the difference between parameters and statistics. We talked about the mean, median, and mode. The most important is the mean. Again, that's an x bar. There's a really tiny bar I don't want you to miss here. Is you add up all the data values and divide by how many there are. The median, we know, is the one in the middle, and the mode is most often, usually in qualitative or categorical data. We talked about variation. One common value for variation is the variance. And the variance, s squared, is the sum of x's minus the x bars. Again, there's a little bar there. Don't miss it. It's kind of small on this font size squared, divided by n minus 1. And we found out that was easier to do if we just made a table where we listed all the values, we listed the mean. The mean's the same all the way down. Subtract, square, add, and then divide. Do a couple of those with a table, and you kind of get that process down real quick. More important, though, is the standard deviation, the square root of the variance. The standard deviation is the square root of s squared, or the square root of that nasty formula. The nice part about standard deviations is it gives us a standard level to compare things with. How many standard deviations away from the mean is a data value? We take the value minus the mean and divide by the standard deviation. Doesn't matter, this is also an x bar. It works with a sample or it works with the population. Both exactly the same. So on the homework, you're going to calculate some means, medians, modes, variations, standard deviations, and the number of deviations from the mean. And then we'll get to Excel later to see how we can do this on Excel.